Hey guys, today I'm going to be doing my video on, LR circuits, more commonly known as RL circuits. So first part of our RL is the R. This stands for our resistor, or resistance. So resistance is equal to the resistivity times the length over the area. It's also equal, it also can be used in these following equations. V equals IR, as well as power equals I squared R, which equals V squared over R. Now you might be wondering, so we're talking about circuits. A resistor in a circuit looks like a nice squiggly line. It's beautiful. So in a circuit it could look like this, and this would be our R, and R is in the units ohm. So the next part of our RL in our RL circuit is the L, which stands for the inductance or the inductor. Now we have a couple of equations that go with our inductance, just the same as our resistance. So it kind of correlates to our capacitors, if you'll remember from our RC circuits. Very similar throughout the equations. So first we have the EMF equals the negative L times the change in magnetic flux over the change in current. Now, the next equation has some derivations, and I'm not going to get into in this video, but I did put them in the slide that will show up next. But overall, it's going to equal L equals N times the change in magnetic flux over the change in current. Our last formula is mainly used with a solenoid. I also put the derivation in the next slide. However, I'm not going to be going into very much detail about this at all. So we have in this L equals mu naught times N squared times the area over the length. The next thing that we're going to talk about is the characteristic time constant, which is represented by our lovely letter tau, and it's going to be tau equals L over R. Now remember that the L is our inductance and the R is our resistance. Now this is going to be in, the inductance has a unit of Henry, which is abbreviated with a capital H, and our resistance has a unit of ohms, with the symbol being a Greek letter that it's omega, yep. And then overall this is your time constant, and so it is measured in seconds or S. Alright, so the next two equations are very important in the RC circuit. So if you look at them, they should look pretty familiar. They look very similar to the capacitance and RC circuits for charging and discharging. So now instead of looking at the change in charge, we're looking at the change of current. So that is represented by our I naught and our I's. I naught in this case, or this one, is going to represent our maximum current. So it's the same for both equations. This I, this current, is the one that we are trying to find in whatever equation, most likely. Now, the rest of this should look exactly the same as with our capacitors. The only difference is that instead of an RC time constant, we have an LR time constant, which is represented by tau. So it's negative T over tau for our exponent for e. So our top equation is going to be for the system with a switch turning on, and our bottom equation will be turning off. Now this may seem like a lot, but I am going to go through a quick example on how these formulas can be applied into an actual LR circuit. So here we go. Now before I get into an actual problem, I did want to point out that this symbol right here is our symbol in a circuit for an inductor. That is very similar to the resistor, but now instead it's going to be almost like how you draw a cloud. Okay, now that we understand what both of these symbols represent along with our switch, I'm now going to assign some quantities to our variables. So our battery is going to have 10 volts. Our resistor is going to have 15 ohms. And our inductor is going to have 20 Henry. So basically, we're going to start by changing our switch to closed. We need to find what our maximum current would be, which, as I said earlier, maximum current can be denoted by I naught. Now, I naught is going to equal V over R. So, in this, we have our voltage and we have our resistance. So all you have to do is plug in. So our I max is going to equal 10 divided by 15. Now that equals 0.667 amperes. Now our next question is going to be, what is our time constant? Remember, that's also synonymous with characteristic time, either one. Either way, we're talking about tau. Now, tau, if you remember, is equal to L over R. Again, we have our L and we have R. So, once again, it's pretty simple. We're just plugging things in. So we have our inductance is 20 and our resistance is 15. Plug that into our calculators and we get that tau is equal to 1.33 seconds. So 0.05 seconds. Now, if you remember before, we had two equations. We had I equals I naught times 1 minus e to the negative t over tau. Then we also had I equals I naught times e to the negative t over tau. Now, which equation do you think we're going to use? Hit pause, try to figure it out. Alright, so basically, our switch is on. So we're going to use the turning on or turned on equation, which is I equals I naught times 1 minus e to the negative t over tau. Again, we're given all the variables, super simple. So we're looking for I. Our I naught was the very first answer to our very first question, which was 0.667. Now we have just 1 minus e to the negative, we have 0.05 seconds over our time constant, which, if you remember from the last part, was 1.33. And now we're going to plug in and solve. We get 0.0246 amperes. If you didn't get that, comment down below, leave me a message. Great things. And I think that that's all I have for